Hello, I'm Yongil, a software engineer from XCENA. XCENA is a startup company that develops CXL memory controllers. First of all, would like to thank the Velox community for giving us this great opportunity to present. Today, I will introduce memory war and what is CXL and how CXL can be used for data processing and share our benchmark results. And after that, my teammate Sungwoo will share the experience how we integrated our data processing library XPlayer with Velox and how Velox can leverage CXL to improve performance. Modern computer systems are increasingly constrained by the memory war. Chiplet-based CPUs have scaled to hundreds of cores, but memory capacity and bandwidth have not scaled at the same rate. As a result, memory capacity and bandwidth per core are actually declining. CPUs spend more time stored on memory, so simply adding more cores no longer delivers proportional performance gains for memory-intensive workloads such as data processing. Meanwhile, DRAM cell scaling is approaching its physical limits, and server platforms are constrained by memory channels and DIMM slots. Scaling local memory is reaching its practical limits. We need a new cost-effective way to scale memory capacity and bandwidth. The cost situation is getting worse as well. CPU cost per gigaflops has kept falling, while DRAM cost per terabyte has stayed high and recently surged due to AI demand. Memory now dominates the total cost of servers, reaching up to 70% of the total server cost. Efficient DRAM use is now more important than ever. CXL is an efficient solution that addresses the memory war. CXL is an industry standard high-speed interconnect for processors and accelerators and memory on top of the PCIe Express physical layer. By attaching CXL memory device into PCIe slots, a server can expand its memory capacity and bandwidth beyond local DIMM limits. The CPU can access the CXL attached memory like main memory using normal load and store instructions. There is no special APIs and no DMA transfers to access memory, just to read and write memory. The key feature of CXL is hardware managed cache coherence between CPUs and CXL devices. This allows CXL integrated accelerators to share data with the CPU more directly without separate data movement steps. CXL also enables memory pooling across servers, allowing each host to allocate memory on demand from a centralized memory pool or use the pool as shared memory across systems. There are two major threats to performance in query engines like Spark and Velox, disk speed and data skew. These are also the key metrics to watch most closely when tuning Spark performance. Disk speed happens when memory runs out. Joins, aggregations, and source, they all maintain large memory states. Shuffle especially requires a lot of memory because of repartitioning. When memory is exhausted, data is spilled to disk and performance drops dramatically. Data skew leads to imbalanced partitions, so some tasks process far more data than others. The heavy tasks struggle with memory, while other tasks remain underutilized. So servers in clusters are often provisioned for the worst case, which wastes a lot of memory. Now, let's look at how CXL can help mitigate these challenges. First, CXL memory expansion provides additional memory capacity and bandwidth to a single server. With the CXL memory expanders, servers can go beyond the limits of traditional DIMM slots and memory channels. A single server's memory capacity can be expanded to tens of terabytes. This increases cluster memory capacity and bandwidth without adding more nodes. It is very attractive from cost perspective. Clusters can have larger total memory capacity and bandwidth with fewer nodes. More memory can delay or reduce disk speed, and fewer nodes can reduce the amount of shuffle data. Another important benefit of CXL is DRAM recycling. Data centers refresh servers regularly, but many DRAM modules are still usable after servers are retired. Because DRAM has a longer life cycle than servers, CXL memory expanders can reuse the DRAMs as an additional memory tier for new servers. Given the high cost of DRAM, reusing existing DRAMs through CXL can significantly reduce overall TCO. Disk skew creates a stranded memory problem. Some nodes run out of memory and spill to disk, while others have still unused memory. Since memory is attached to each server statically in conventional architectures, this imbalance is difficult to rebalance dynamically. Microsoft said the average of 25% of DRAM is stranded at Azure. CXL memory pooling can be a solution to this problem. Hosts can borrow memory from the shared memory pool on demand and return it after use. It allows those to meet peak memory demand without over-provisioning every server and reduce total cluster memory. A CXL memory pool can also be used as a shared memory across multiple hosts. By pricing shuffle data in the CXL shared memory, it can reduce network-based transfers, so shuffle overhead can be significantly reduced. CXL introduces new tiers in the memory hierarchy. We now have memory expanders and shared memory pools between main memory and storage. CXL memory expanders increase capacity and bandwidth within a server. CXL memory pools extend the memory hierarchy across multiple servers. These new tiers give us much larger capacity, but also have higher latency and lower bandwidth than main memory. Therefore, software needs new optimization strategies that are aware of this new memory hierarchy. More broadly, this calls for a shift toward memory-centric computing. The conventional computing model is CPU-centric computing. Wherever the data resides, it eventually brought to the CPU for processing. Because CXL memory typically has higher latency and lower bandwidth than main memory, when large data sets are stored in CXL memory and CPU process them directly, performance is often bounded by PCIe bandwidth. This is where memory-centric computing comes in. Instead of moving data to the CPU, we move computation closer to the data. An accelerator inside the CXL device can filter and process data locally and return only the final results to the CPU. This reduces data movement significantly, so we can improve both performance and power efficiency. The key idea is simple. Move computation closer to the data, not data to the CPU. This is MX1. It is a computational memory we designed for memory-centric computing. It is also the world's first CXL memory device to support the CXL 3.2. MX1 is based on PCIe Gen 6, and it supports 4 channels of DDR5 RDIMMs, providing up to 1 terabyte of memory capacity per device. It integrates 3,000 RISC-V cores for massively parallel computing to the data stored in the CXL memory. It also has 48 vector processing engines to accelerate vector search. These are our prototype device spec, and an upgraded production version will be released early next year. You can request the device samples at our homepage if you would like to experience memory-centric computing. MX1 is basically CXL memory expanders, so it provides additional memory to the server, and CPU can access MX1's memory as its own memory. MX1 also shares the virtual address space with the host process. When host process allocates CXL memory and maps it to a virtual address, it also copies the page table entry to the device's MMU, so both sides can reference the same pointers in the same address space. This is not the same as GPU unified memory, which relies on phase forks and migration. Because MX1 shares the same memory and page table with host process, there's almost no overhead. This also allows MX1 to remove the data input and output stages before and after offloading. No separate device memory allocations, no express data transfers, and no pointer swizzling and swizzling. This simplifies the offloading process and significantly reduces data movement cost. This is our microbenchmark research on Intel's latest generation Xeon server. We compared one CPU NUMA node with one MX1 using some of the representative query processing operations, such as compression, decompression, and packet decoding, aggregation, and filter operations. We evaluated 3 execution models: CPU processing data in main memory, and CPU processing data in CXL memory, and MX1 memory-centric computing. MX1 achieved up to 4.7 times higher throughput and 18.7 times better energy efficiency than CPU processing data in CXL memory, and up to 2 times higher throughput with 6.2 times better energy efficiency than CPU processing data in local main memory. Since this is only one-to-one comparison, and each socket supports up to 4 CXL devices, we can expect up to 4 times the great performance in a full configuration. Now, I'll hand it over to Sung.
Okay, thank you. Hi. In part 2, I'll be talking about how we are extending Velox for CXL native query execution. Before we go any further, I'm Sung. I'm a software engineer at XCENA, and I lead the development of XFlare. So what is XFlare? It's a CXL native data analytics library we're building at XCENA. Think of it like a QDF, but for CXL. So it's for easy adoption of CXL in your favorite data processing platforms. There are a few characteristics. It's written in Rust, first of all, and it's highly asynchronous to overlap the CPU work and memory-centric computing. It uses open formats, arrow for in-memory, and Parquet CSV JSON for files. It takes care of hardware orchestration for you, such as CXL memory allocation and kernel launching. It is a closed project for now, but once our MX1's production-grade version becomes generally available early next year, we will be opening to the public. So we wanted to bring in memory-centric computing to Velox by integrating XFlare. And when we designed the integration layer, what we wanted to do was create an extension instead of modifying the Velox core directly. So, well, thanks to Velox's nice extension framework, driver adapter, we were able to pull that off and extend Velox for memory-centric computation very easily. We call our integration layer collagen. So try to imagine how surprised I was yesterday when Pedro talked about their collagen project, and I thought the name was unique enough, but I guess not. So our collagen layer accepts execution plan and arrow batches and hands them off to XFlare, which offloads computation to MX1's 3000 RISC-V cores. Driver adapter allows extension to replace a sequence of operators with a custom operator. So at each driver initialization, we scan for a sequence operators that we can offload to XFlare, and then we replace it with our custom operator, which sort of acts as a facade that just relays the request to XFlare core. There was a tiny challenge we faced we need to pass the operator context from C++ velox to Rust xflare. So what we decided to do was create a custom protobuf, much like Substrate. So we encode the operator context in protobuf and then offload it to xflare driver. We also needed to transport velox's column across the collision. Since velox's column vectors are arrow compatible, we leverage that. So in our custom operator, we export the velox column vectors into arrow CABI format, and then we export it to xflare. And we import that into our own column vector format. And then when we are sending back the intermediate result back to velox, we just go just the reverse process of it. That's me last year. After getting our MX1's prototype device, we were able to showcase our devices at OCP Global Summit and Supercomputing Conference. These are the biggest events for data center and infrastructure players to show their latest and future technologies. We did a live demo of TPC-H queries on Apache Spark through Gluten and Velox and then xflare using memory-centric computing. And if you think about it, it's quite remarkable because Velox and their idea of composable architecture opened an opportunity for hardware acceleration companies like us to test our device against very famous data processing frameworks like Spark. So this could have been like years of software project, but we were able to pull that off within a few months. So thank you, Velox. I want to conclude my presentation with a maybe new development idea. So from our extension journey, we came to believe that Velox can really benefit from having a CXL-aware memory allocation. So let me walk through two scenarios to illustrate that. In the first scenario, when memory pressure hits the limit, Velox goes through a memory arbitration process, and eventually some operators ends up spilling their intermediate data to the disk. With a CXL-aware allocator, you can delay and reduce the disk spills, which can benefit Velox for two reasons. The one, you're not spilling anymore, and then two, you can also reduce the cost of memory arbitration process. You can also get smart with this and store data in different memory tiers according to your access pattern. So hot data like hash table can stay in the local DRAM, whereas warm data like row containers can stay in the CXL memory so that you can expand the memory and then reduce the CXL latency. The second scenario is allocating the value stream's row vector directly in CXL memory. Value stream operator is an operator that converts Spark's row-oriented data, input data, into Velox's column vector format. With current implementation, value stream allocates the row vector in the host main memory, which is quite inconvenient for us in memory-centric computation because our MX1's cores cannot access the host DRAM directly. So to start the memory-centric computation, we are forced to copy the data in the CXL into the CXL memory. But with the CXL-aware memory allocator, you can allocate the row vector directly in the CXL memory, and you can just start the memory-centric computation right away. So that's the approach we actually take when we offload table scan operator, for example. We allocate CXL memory for Parquet reader to load the pages from the disk, and then we just start decompression and page decoding right away. We can think of some hurdles to building a CXL-aware allocator in the current implementation. The current implementation doesn't allow the custom allocator to be pluggable. So we are gonna have to do like a driver adapter approach in this. And also CXL memory is a separate memory resource from host DRAM. So we are going to need to have a custom memory manager and a memory arbitrator. But we think that it's worth a shot anyway. So we will be communicating with the Velox community about this idea, and hopefully we'll get to make a contribution. So here are the things that you should take away from this presentation. Analytics is hitting a memory wall, and memory-centric computing can change this with higher performance and better energy efficiency. And this is why we believe that Velox can benefit from adopting CXL memory-centric computing. So that's it. And if you have a question about this presentation, memory-centric computing, or CXL in general, please come find us during the lunch break. Thank you.
Okay, wait, before people head out to lunch, we want to try to do a conference picture. So I'm going to be super annoying and ask everybody to move to the middle. You don't have to sit, just stand. I'm going to try to take a picture from the stage. Thank you.